about the scaling of MS devices and then wrap up the MS section chapters. And from next week we're going to discuss about the bipolar transistors. Okay. Now ideal scaling of MOSFETs. Ideal scaling of MOS. We want to scale down the MOS transistors source and drain and gate to have a benefit, many benefits, but we're going to discuss about the benefits by scaling down the MS transistors later. But anyway, if you want to scale down the MS transistors, there are two. Basically, what we want to reduce is the lateral dimensions, right? But if you want to reduce the lateral dimensions, you have to do something on these vertical sections, like gate thickness and gate oxide thickness and source and drain doping things. That is the dimensions related to the vertical sections, right? So the scaling means we want to reduce the lateral directions of MS transistors, but in order to do that, we have to make some changes along the vertical sections of MS transistors as well. Now, in principle, we want to keep electric field constant with this scaling down, okay? Because if you change the electric field by scaling down the device, then many physical phenomena like breakdown and saturation, velocity saturation, which is related to the drain current. Those are physical parameters is going to be changed if you change the electric field, because the physics inside the MOS transistor is going to be changed. So even if we want to change the lateral dimensions, we want to keep the electric field constant. That's that's a basic principle. For example, if you want to change the gate length here, then we want to change the gate drain voltages. Okay, because the electric field is Vd over L, right? So if you scale down the L some factor S, then you want to reduce the drain voltages as well with that scale to keep the electric field constant between source and drain. Okay, that is the basic principle. But in practice, we have three ways to scale down the device, and that is a constant electric field that we have just discussed here. And also we can do some constant voltage. That is the, actually, this is the ideal scaling principle. And constant voltage, when we scale down the device, that is the industry practice. They want, in the industry, they want to put the input as 5 volts all the time. If you change the input voltage, then you are going to change whole lot on the circuit. So in the industry, even if you scale down the device, you want to keep the voltage constant, input the constant, to make the things simple. These days, the input voltage is about 3 volts. It is changed, but in the industry, they want to keep the constant voltage. And we can have a quasi constant voltage. That is the intermediate scaling between a constant electric field and constant voltage. So say scaling law and constant electric field, constant voltage, and quasi constant voltage, then for example, say dimensions. We scale down by the factor S, okay? Then the gate oxide has to be scaled down to S by S factor if you want to keep the electric field constant, and if you want to keep the voltage constant, then gate oxide is going to be square root of S, okay? And this is going to be S. And the doping level, this doping is source and drain, they are all scaled by S, factor S. And then voltage, constant voltage is going to be 1, but electric field and quasi constant voltage scaling law, the voltage has to be scaled square root S, okay? And in this class, we're going to discuss about the constant electric field only, but we just compare the other two just for the comparison. And if you said this is the drain current, this drain current is available. ID here is available drain current. Available drain current. Available drain current means the drain current is going to be saturated. It's limited by the saturation things, and those are physical parameters. Limited by preset, right? That we have discussed before. And this is the scaling factor, and here is 1, and then it goes down, something like that. Now, by scaling down the device, according to the quasi, let me see, let me give you the data for the constant electric field case. Constant electric field case, for example, it goes down like that, okay? For example, constant electric field case. Now, what happens if you use the constant voltage, like industry practice, then it's a little bit higher than this, but not over this, but it is something like this, constant voltage, okay? And then in quasi case, it goes somewhat something like this. This is a quasi constant voltage. The available drain current we can have from the MOS device, we are going to have different values for the available drain current according to the scale down principles that is applied for the miniaturization of the MOS device, something like this. But in principle, as I said, this constant electric field is related to the ideal scaling, okay? Because when you maintain the electric field constant, then the physics inside the MOS transistor is going to be the same. So we do not want to change the physical reactions, physics inside the transistor change by scale down. So that's why we want to keep the electric field constant, okay? So let me just go back to the constant electric field. Constant electric field for ideal scaling. In principle, what we are going to do is all linear dimensions. All linear dimensions is going to be scaled by 1 over S, okay? S is the scaling factor. And that is greater than 1, okay? And number 2, all voltages, like threshold voltages and drain voltages, sub-threshold, substrate voltages, all these voltages are going to be scaled by 1 over S to keep electric field, which is voltage divided by the distance, keep its electric field constant, okay? And number 3 is the important thing, is all doping levels scaled by S. So number 1 and number 2 is obvious, and then let's just think about the number 3 a little bit. Okay, let me give you an example. What does that mean? All right. For example, the depletion width, WB, is related to the equation Q and A. Right? This is the equation that we have. Now, if you scale down, we scale down the device. Let's see what happens to this WB. Okay, the scale down means the dielectric constant and the built-in potential. We just keep the built-in potential the same. Now the voltage is going to be scaled down by the S, and then we want to keep the substrate current doping level by scale factor S, like this. And then we end up with WB is going to be scaled by S, something like this. Okay? And the threshold voltages also we can have equation something like this that we have discussed, right? And this thing, when you scale down, means QF. Now C naught is going to be S oxide, tin oxide, right? If you scale down the thin oxide by S, then the capacitor, oxide capacitance is going to be changed in this fashion. And then you have Q, increase the substrate doping level by a scaling factor, and the substrate voltage is going to be scaled by the factor, and then you apply all these scaling factors to this equation, then you end up with threshold voltage is going to be scaled by S like this. This means when you scale down the device to keep the electric field constant, then the threshold voltage is going to be go down, going to be reduced by the scaling factor S as well. Okay. Now, what about the drain current? If you scale down the drain current, we had this equation before, right? Then if you scale down this, then the drain current is going to be scaled down to by the factor S. This is a sad story, actually. Okay. So by scaling, we have those parameters going to be changed accordingly. Okay. If you want to keep the if you want to keep the electric field constant. Now benefits. Why we want to scale down the device? The obvious thing is layout density, which is related to the integration level. That is gates per millimeters square. I have statistics for the years 1977, 1980, and 1985. So this class note was made a long time ago. Now it's 2016. So this values is pretty much different. But of course, you cannot extrapolate these numbers linearly, but I think we have a tremendous increase in the layout densities these days. But anyway, I just give you the idea of what kind of a benefits we can have by scale down the device. So I just give the data, all the data, the speed, power, product. That is 1 and 0.2 and a 0.01. So the speed is going to be the power dissipation, power consumption, if you like, is very much reduced by scaling. Gate delay, 0.5, 0.1. Power supply voltage, 5 volts, 3 volts, and 0.0 volts. Obviously, these days the power supply voltage is not going to go down to the 1 volts. I think it's around the 3 volts these days. Channel length, micron, and 3.5 and 2.0 and 0.7. I think this is on 1985, it's just a prediction that was made around the year is 1980. And obviously, the channel length these days is a sub-micron, and it's about the right values right now, not in 1985. And the T oxide thickness, angstrom, 700, 400, and 100. These values right now we are using. We has a equipment limit. We cannot make oxide thickness less than 100 angstrom, even these days. So that is a prediction that has been made in 1980s. So this is just overestimated, I think. But you can just get the feelings why we want to get the scale down the device, okay? So let me summarize. The scaling device circuit parameters and a scaling factor and dimensions. All those things is going to be scaled by 1 over s if you want to keep. This is the case for the constant electric field scaling, okay? And substrate doping, Na is going to be scaled S. It means the substrate doping has to be increased by the factor S, right? And the supply voltage V voltage is going to be reduced by 1 over S. Supply current it's going to be reduced to 1s, and the parasitic capacitance per the capacitance WL over TR, it's going to be reduced. And gate delay 1 over S, and power dissipation one over S squared. Okay, this is good, and the power speed product is going to be 1 over S to the third. Now let me give you the problems that we can have by this scaling. We have these benefits. We have, except this supply current thing, all the other factors are the benefits we can get out of the scaling the MOS device, okay? Now, what kind of problems we can think by this scaling? Even if we don't have any problems, we cannot reduce the device to the limit. It's always limited by the process, okay? Manufacturing processes like lithography, etching, deposition, all those things are limited by the physical process, not by the problems that we are going to discuss here. But anyway, let me just give you problems with ideal scaling. Firstly, in our earlier discussions, built-in potential, flat band potential, and work function difference has not been taken into account. But if you scale down the device more and more, now these values, change in these values is going to be important, maybe. So we have to find a way to take those changes in these values to be implemented in the scaling law, okay? And threshold voltage it's going to be dependent. We have seen this, right? It's going to be dependent on W, L, and drain voltages, which cannot be not been predicted by simple theory. So we have discussed about this, right? The effect of geometry to the threshold voltages. But we just didn't know how it will affect those geometric factors to this threshold voltages, but we don't know the limit, how far we can apply that, you know. So even though the physical process will limit the scaling of the device, but in principle, we cannot understand the physics inside when we had to the limited the scaling of the device. Okay. And this is also we have discussed for in other words, we do have threshold current. Okay. And ID is controlled by VD rather than VG. Okay, it means that when you scale down the device, now VD is more important to control the current between source and drains rather than the gate voltages. It used to be the gate voltage who controls the current between source and drains, but when you scale down the device, now the VD becomes more important than the VG. Okay. And we have discussed about the saturation thing, the critical electric field for mobilities, right? So that's is not the linear velocity is not and the mu is not constant. Beyond the critical electric field, and we have a saturation velocity, so that the drain current is not controlled by the velocities that has appeared on the equation, but this velocity, the current is going to be controlled by the saturation of the electrons. Like the current and voltage, gate voltage, we usually have this value, this. Like this, but as you have seen, this is the current by the saturations. Okay, so the drain current is going to be controlled by the saturation phenomenon rather than the simple equations that we have developed for the drain current. So when you scale down the device, physically we have a limit to scale down the device, but physically limit besides the physical limitations, we have some deviations, I should say, deviations from the simple theory when you get down the device small and small, right? So all those things has not been, some of them have been cleared and some of them are still under study, but I think these days the MS devices, the scale down of the MS device is mainly limited by the physical processes, like lithography and deposition and etching techniques and things like that. And we have 256 mega DRAMs these days. I think that is the limit that we have currently. And if you want to scale down more, then you need a special technique for that, which is not appropriate for the mass production yet. Okay, let's see. This is the end of MS operation principles, discussion on the MS operation principles. And next week, on Monday, from Monday, we're going to discuss about the bipolar operation principles of bipolar transistors. And if we have a time in this semester, probably we can go back to other transistors, MS transistors like gallium arsenide and thin film transistors and DRAM and LDD structures and so forth, okay? But I don't know the timing, so let's just start the bipolar transistors from next Monday. Okay, have a nice weekend.